Bushings are subjected to high dielectric and thermal stresses, and bushing failures are one of the leading causes of forced outages and transformer failures. Reviewing of transformer failure data shows failure data from North American utilities have shown they can account for up to 40% of transformer failures. This data also shows that 52% of bushing failures are violent, in that there is an ensuing fire and considerable collateral damage. The two most common failure mechanisms are moisture contamination and partial discharge. Recent notices have been issued by bushing manufacturers concerning the effects of corrosive sulfur in the bushing oil causing PD in bushing failure. Moisture can enter the bushing through deteriorated gasket material, cracks and loose terminals. Moisture will cause an increase in the dielectric losses and consequently an increase in power factor. As the deterioration in the bushing insulation continues, there will be a breakdown in the capacitive layers and tracking will become apparent, which produces partial discharges. The method of detecting bushing insulation deterioration is well understood and traditionally offline tests have been performed. Power transformer bushing testing and monitoring. Little can be done for maintenance on bushings E.G checking oil level or SF6 level. Many bushings do not even use oil or SF6. Hence, they need to be replaced periodically to avoid catastrophic failures. To plan the replacements, the bushings can either be tested periodically by taking outages or be monitored online. Online monitoring provides a much more cost-effective and reliable way to make informed decisions on bushing replacements. Offline and online power transformer maintenance practices for bushings. There are offline periodic testing practices and online monitoring practices for transformer maintenance. The online continuous monitoring practice has been gaining traction due to high return on investment and effectiveness in not only avoiding failures but also reducing time-based maintenance costs. The offline period maintenance practice for bushing may include visual inspection, infrared inspection, cleaning using different methods, power factor testing tan delta or tan delta, and capacitance testing. Different type of bushing can be seen in this table. In extreme cases, a dielectric failure in a bushing can result in total destruction of the high-voltage equipment in power transformers. For instance, losses stemming from an event of this type can be worth a few hundred times the unit cost of the bushing that originally caused the problem. Among the different existing types of bushings, the condensing bushing stands out in high and extra high voltage applications. In these bushing, the insulating body is made up of a staggered arrangement of several concentric cylindrical layers of insulating material and layers of conducing materials for the purpose of making the electric field as uniform as possible. The innermost conducing layer may be connected to the main lead, in order to increase the radius and reduce the electric field in this region, also reducing the intense electric fields that may be caused by surface roughness on the main lead. The outermost conducing layer is connected to the flange of the bushing that, in its turn, is grounded. The intermediate conducing layers are insulated, with floating potential. Bushings are accessories used in high-voltage equipment for the purpose of providing safe passage for electric current from the external environment to the interior of the equipment, as well as providing the necessary insulation in relation to the casing of the equipment. A few of the more common examples can be found on power transformers, reactor shunts and high-voltage circuit breakers. Despite being accessory to the different equipment types mentioned, and in general being of much lower unit cost as compared to the overall cost of the equipment, bushings perform a function that is essential in operating the equipment. On the other hand, bushings are subject to considerable dielectric strains, and a failure in their insulation may result, not only in damage to the bushing itself, but also to the entire equipment to which it is associated. Siger International Council on Large Electric Systems. Transformer reliability study shows that bushing failures continue to be one of the leading causes of transformer failures around the globe. The study also shows that bushing failures were the cause of over 1/3 of the transformer failures involving fires or explosions. Due to the financial impact a catastrophic transformer failure can have, many utilities are turning to online bushing monitoring to identify deteriorated bushings earlier and prevent transformer failures. One can see in this table online bushing monitoring methods comparison, which is done through capacitance, balance current and source independent, advantages and its disadvantages. Online bushing monitoring systems have been successfully used by the utility industry for over 20 years. They have a proven track record for being able to identify degrading bushings early in the failure process. By providing early warning, users have additional time to plan and schedule an outage to replace the bushings. While there are many users that have successful online bushing monitoring programs, some users cite problems with false alarms from the monitor. While there can be multiple reasons for a false alarm, sensor-related problems are one of the more common complaints. The use of properly designed sensors and correctly installing the sensors can improve the reliability of the online monitoring system. Why bushing monitoring? Among the reasons for transformer outages, bushing failures are often the cause. It is common to find a bushing testing poorly, and there have been many noted total transformer failures due to bushing failures. One reason may be because bushings are often tested offline to measure capacitance, dissipation factor, and power factor. Bushing monitoring system advantages. Early detection of a degradation of bushing insulation and internal layer breakdown. Monitoring power factor/dissipation factor and capacitance at nominal voltage. Applicability for condenser bushing type and other OEMs. High accuracy measurement can be achieved by using parallel measurement of up to 6 bushing leakage currents. Optimized and purposive maintenance strategy reduces outage costs. Comprehensive online condition monitoring system possible for transformer and bushings, in combination with transformer monitoring and diagnostic system. Sensor design. IEEE standard C57.19.100, IEEE Guide for Application of Power Apparatus Bushings offers the following guidance when selecting a bushing monitoring system/sensor. Bushing monitors are installed on bushing cap taps to allow for online testing and monitoring. These devices allow for continuous monitoring or periodic testing of bushings without removing the bushing from service. Since the monitors replace the existing cap tap cover, the user should ensure proper fit of the monitor to prevent moisture ingress into the cap tap. Sensor types. Resistive style sensors utilize resistors connected between the bushing tap and ground as the primary method to limit the voltage from the test tap. Should the resistors fail, metal oxide varistors MOVs or similar over-voltage protective devices limit the voltage output from the tap to acceptable levels. Current limiting resistors in series with the MOVs can help to prevent MOV failures. Since the test tap of the bushing is solidly grounded through resistors, this type of sensor closely matches the original bushing design where the C2 capacitance is grounded when in service through the tap cover.